Hello statistics students, this is Emigh, and this video is our discussion on section 8.3, testing a claim about a mean. Before I go to our first example, I want to review that when you're testing a claim about a proportion, you are running inverse norm to find the critical value, and the other program you're running is one prop ZTest, and that will get you your test statistic as well as your p-value. Okay, now let's switch it to this section, 8.3. We're going to be testing claims about means. Means, we have to debate, or we have to decide between Z or T. So based on sigma, I'm going to go ahead and go this way. Two cases. If you know what sigma is as the main requirement, you are still going to be running inverse norm. And you're going to be running the Z-test. If sigma is unknown as the main requirement, these are the same requirements as they were for confidence intervals. If sigma is unknown, you're going to be running inverse T to find a critical value, and you're going to be running the T-test to find your test statistics and your p-values. So before we go to our first example, focus on this slide. Look at when the claim is about a proportion, these are the two main programs you're looking at. When the claim is about a mean, you're going to have to decide, am I running inverse norm and Z-test, or am I running inverse T and T-test? Main deciding factor is the knowledge of sigma or not. All right, let's try our first example. Listed are the measured radiation emissions for a sample of cell phones. Use a 0.05 level of significance to test the claim that cell phones have a mean radiation level that is less than 1 watt per kilogram. And they very specifically are requesting that we use the critical value method. Okay, to start our hypothesis test, we always start with two capital H's, sub naught and sub 1 for the null hypothesis and alternative hypothesis. Okay, first decision we have to make right now is if we're going to put the letter P for proportions, mu for means, or sigma squared for standard deviations and variances. Well, we are being asked to test the claim about means. So you're going to put mu. Null hypothesis always gets an equal sign, and time to make your next decision. Which inequality do you put for the alternative hypothesis? Okay, well, the claim is that cell phones have a mean radiation level that is less than 1 watt per kilogram. So we use the less than symbol there. Okay, 1 watt per kilogram is what we're judging this against. They're claiming that it's less than that. Okay, critical value method, we need a graph. 0 in the middle. Okay, time to make your next decision, and you're either going to label your horizontal axis with the letter Z or the letter T. Okay, and the way you decide is we're looking to see if we know the population standard deviation sigma, and we do not. So we are going to go with student T distribution. Okay, next decision we have to make is to cut off the left tail, the right tail, or both of the tails. And since the inequality was the less than sign, then we cut off this tail. Creates that shaded region right there called the rejection region. Okay, the critical value is what creates that rejection region. So we're going to find that critical value right there. So it's going to be negative, as you can see, because it's to the left of 0. And we're going to find that critical value by running inverse. And your options at this point are inverse norm or inverse t. And we've already decided that we're using student t distribution. So inverse t. All right, let's do this together. Pick up your calculator. Turn it on. Clear your screen. All right, I want you to hit second, distributions. Scroll down to inverse t. It's a capital T. And open that program. The first thing it wants from us is the area. My calculator always requires the area to the left. So that would be that little shaded region. What is that area? Well, the rejection region gets the area of the significance level alpha, which is 0.05. Okay, so your first input on area is 0.05. Next thing the program is requesting from us is the degrees of freedom, the lowercase d, lowercase f. And for student t distribution, that's always 1 less than the sample size. Well, what is our sample size? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Sample size is 11, which means degrees of freedom is 10. 11 minus 1. So next input for that program is 10. And that's all the program needs from us. Just those 2 inputs of area and degrees of freedom. Now go ahead and run that program. And that number you see on your screen right there is called the critical value. And we get negative. That's good. If we didn't get negative, we made a mistake. And I'll just go to 3 decimal places. I don't think it requests a certain number. I'll go to 3. Okay, so our critical value is negative 1.812. Okay, next thing we need to do to implement the critical value method is find the test statistic. And we find the test statistic by running the t-test. Other options were 1-prop ZTest and ZTest, but because we didn't know sigma, we've already determined that we're using student t distribution, so we're going to run the t-test. Okay, do this with me. Pick up your calculator, hit stat, scroll over to tests, scroll down to t-test, open that program. Okay, the very first thing that this program requests from us is, would we like to run the program off of data or off of the statistics? If you look at our problem, we have been given the data, the 0.38, the 0.55, the 1.54. If we were given the stats on that data, we would see stuff like x bar equals, lowercase s equals. But we were given the data, so you need to make sure data is highlighted. Okay, so my data is highlighted now, and the next input that it wants from me is mu sub naught, which we did in step 1. It is 1.00. Okay, if you scroll down, the next thing you see there is it wants to know which list we entered the data into. Okay, well, that's a little bit of a problem because we haven't entered the data into a list yet. So we're going to do that right now. Okay, do this with me. Hit stat. We always put the data where it says edit. So hit edit. In L1, I want you to put those 11 values. 0.38, 0.55, 1.54, 1.55, 0.50, 0.60, 0.92, 0.96, 1.00, 0.86, and last 1.46. Okay, now we're going to go back to our test. Do this with me. Hit stat. Arrow over to where it says tests. Reopen that t-test. Data should still be highlighted. The 1.00 should still be there for your mu sub naught. L sub 1 is still there, and that's where we put the data, so we're good. Frequency is 1. And the last thing that this program needs from us is to tell it, it wants us to tell it what we used as our alternative hypothesis. We used the less than sign. On your screen it looks like this. Make sure that is highlighted. Okay, go ahead and run that program. And that top line of output says t equals negative 0.48, approximately 5. So that is called our test statistic. And that is t equals negative 0.48. And I went with 3 decimals last time, so I'll go with 3 again. 0.485, negative 0.485. Okay, I'm going to change colors just so you can see this more clearly. What I'm doing right now is putting the test statistic on the horizontal axis. Negative 0.485 is closer to 0 than negative 1.812. It's right about here somewhere. I'm going to put TS, so you know that that is my test statistic, and that is a value of negative 0.485. Okay, our computation work is done. There are no other programs to run, nothing left to compute. Only thing there is to do now is write down our decision and then write our conclusion. Okay, so here we go. Our decision is to fail to reject the null hypothesis. The reason why is because our test statistic is in the unshaded region. Remember that this little region right here is called the rejection region. Our test stat isn't in the rejection region, so we're going to fail to reject the null hypothesis. Okay, now we have to write our final conclusion. We always start with the word there. Blank number 1. And if you need to look back at the last video, that's where I really break down how to fill in these 3 blanks. Okay, blank number 1. It's either going to be the word is or is not. Based on our decision of fail to reject, it's is not. Had our decision been reject, it would have just been the word is. Okay, there is not, and then we always write evidence. 2, second blank. Here we have to make a decision. We have to write the word support or we have to write the word reject. It is very tempting to think that this blank right here depends somehow on our fail to reject the null hypothesis or reject the null hypothesis decision, but it does not. This blank right here depends way back when the original claim. If the original claim contained equality, like this, this, or this, we would say the word reject. If our original claim does not contain equality, so this, or this, we say the word support, and our original claim was strictly less than. That means it does not contain equality. It doesn't say like less than or equal to, and therefore we write the word support. Okay, there is not evidence to support, then we write the claim. That. And then we just, the very last blank, the third one, is just restating the claim. The claim that cell phones have a mean radiation level that is less than 1 watt per kilogram. kind of shorthanding it just for time and space. Okay, next example. Ooh, you want to see it all? I hand wrote all of that, but okay, let me back up a little. What I'm going to do right now is completely erase everything that I just wrote in red and blue, and that way you can just see it. That is what your null and alternative hypothesis would look like. It would be a left-tailed test, second distribution, inverse t. That's how we got our critical value of -1.81. Stat edit, enter our data into list 1 and run the t-test. That's how we got our test statistic of -0.4849. In a left-tailed test, the test statistic would not fall in the rejection region created by that critical value. And that's just writing down what the graph was explaining visually. That means our decision should be fail to reject the null hypothesis. And there is that conclusion written up. Much nicer than me writing it with my finger. So, two ways to look at that solution. This one really takes out a lot of the sloppiness that I added, but at the same time, all that stuff I was adding kind of lets you see the train of thought I was on. So whichever works for you, maybe take a look at both until you figure out what you're more comfortable with. The only thing I would probably add to this would be a graph. I think the rest of it's here, but I think seeing that left-tailed test, seeing the -1.81, as well as the test stat right there of -0.48, shows visually why we decided to fail to reject the null hypothesis. Okay, next example. It looks very similar, but I did switch it up. Listed are the measured radiation emissions for a sample of cell phones. Use a 0.05 level of significance to test the claim that cell phones have a mean radiation less than 1 watt per kilogram. So all of that was the same, and here's where I made the adjustments. Assume that sigma equals 0.480 watts per kilogram, and use the p-value method this time. Okay, so with those two changes, you start out exactly the same. Okay, h sub naught, h sub 1, mu because the claim is about a mean, equal sign because it always is in the null, less than sign because that came straight from the wording of the claim, 1.00 watts per kilogram still. Okay, everything looks the same so far. Now, with the p-value method, we do not typically draw a graph. You can if you want to compare the areas, but you don't need to. The visual on it is not as vital as it is in the critical value method. So all we have to do is run our test. Well, we have to decide which test to run. Here are your 3 choices. I'm going to make this multiple choice for you, okay? Do you want to run one prop ZTest? Do you want to run the t-test? Or do you want to run the ZTest? It's only 3 we have so far in this class, at least. So pause the video. Look back if you need to. Figure out which test you're supposed to run here. Okay, welcome back. If you chose the Z-test, good job, you chose correctly. One prop Z-test was out because the question is not about proportions, it's about means. And then how to decide between Z and T, this knowledge of sigma right there being 0.480 is what told me don't need to use student T distribution. I can use Z test because I know the population standard deviation, which is denoted by the lowercase Greek letter sigma. Okay, so let's run the z-test. Gonna hit, let's see, I think I have it typed on here. Let me erase the writing I added. There we go. Okay, so let's do this together. Pick your calculator up, turn it on, clear your screen, hit Stat, scroll over to Test, scroll down to the z-test, which is actually the first one. Open the z-test. Decide if you're going to run this off of data or off of stats. So we have to select now if we're going to run our test off of data or off the stats. And we have the data here, so make sure data is highlighted. Mu sub naught is 1.00. Sigma, mine has a 26 right there, that auto-populated from an old question. Make sure your sigma is typed in as 0.480. L sub 1 still contains my data from the last example. If you're coming back to this video late and your data is no longer in L sub 1, then you need to put it there right now. So you can hit Stat, Edit, enter those 11 radiation levels, and then bring yourself back to Stat, Test, Z-Test. Frequency is 1. Alternative hypothesis is the less than sign. You made that decision based on the claim. And go ahead and run the Z-test now. Okay. Top input, Z equals negative 0.427. That is called your test statistic. Should anybody request that from you? P-value method does not require the test statistic though, so you're not going to need that. The next line has the output of P equals 334 approximately. The line after that gives you X bar, so that's your sample mean, so the average radiation emission level of those 11 values there. Next is your lowercase s, so that's your sample standard deviation. And then lowercase n is your sample size. But the only thing we need on this output screen, if we're asked to use the p-value, the only thing we need is the p-value, which is p equals 0.334. Okay, so what we do now is we take the p-value and we compare it to the significance level. P-value is 0.334. Significance level is 0.05, and so our p-value is higher than our alpha, our significance level. So the little rhyme goes, P is high, the null will fly, and if the null will fly, there's no need to reject it. So we would fail to reject the null hypothesis. I'm going to take my handwriting off the screen and do the typed in solution instead. So here it is. P-value equals 0.3364, which is greater than the significance level of 0.05. And here's that rhyme I just said. P is high, the null will fly. Fail to reject the null hypothesis. And now time to write our conclusion. Always start out with the word there. First blank is not sufficient evidence to. Next blank is support. Then you always say the claim that, and then you restate the claim. Cell phones have a mean radiation level that is less than 1 watt per kilogram. Okay, got one more example to do here for this section, and I'm going to do the methods side by side. Okay. Test the claim that an adult population of one town has a mean annual salary of $30,000. A sample of 17 people had a mean of $22,298 and a standard deviation of $14,200. They want us to use a significance level of alpha equals 0.05. Okay, as we know, the two methods start out the same with two capital H's, sub naught, sub 1. Time for our first decision. P, mu, or sigma. And this claim is about, tests the claim that adult population of one town has a mean. So since the claim is about a mean, we write mu. Null always gets equals. Alternative has to do with the wording of the claim, that an adult population of one town has a mean annual salary of $30,000. They're claiming that it equals $30,000. They're not claiming that it's greater than $30,000 or less than or equal to. They're claiming exactly $30,000. So that means that their claim is the equal sign. But as you guys know, you're not allowed to use the equal sign in the alternative hypothesis. You're only allowed to use greater than, less than, or does not equal. So you're going to use the complement of equals, which is does not equals. Okay? All right, and then it's $30,000. Okay, next thing for the critical value method would be to sketch a graph, and it's decision time again. Z or T on the horizontal axis, and that is going to be based on our knowledge of the population standard deviation sigma. Now, this gets really tempting right here because it says a standard deviation of 14,200. So it's easy to go, oh yeah, they told me the standard deviation sigma. You're close. They told us the standard deviation, but it's not sigma. That standard deviation of 14,200 came from a sample of 17 people. So this is lowercase s, sample standard deviation. It is not sigma. So we need to use the student t distribution. Okay, next decision. Cut off the left tail, the right tail, or both of the tails. And the answer is both, because our alternative hypothesis is does not equals. So we have two rejection regions here. So we need to split our alpha. Our alpha is significance level of 0.05. We need to put half of it over here and the other half in this tail over here. Okay, let's find that critical value, the one that created those rejection regions, by running inverse T. And the area to the left of the critical value you're interested in. So I'm going to go with 0.025. So I'll find the negative critical value first. And the next thing that program requires from us is the degree of freedom, which is 1 less than 17. 1 less than the sample size, so it's 16. All right, let's do this together. Calculator's out. Hit stat. Ooh, wrong. Clear. Hit second. Hit distribution. Scroll down to inverse T. Open that program. Give it an area of 0.025. Degrees of freedom is 16. Run that program, and that number you see on the screen is the critical value, negative 2.12 I'll go with, approximately. It's positive 2.12 is the critical value that created the rejection region on the right side of 0. So positive 2.12 and negative 2.12 because this is a two-tailed test. All right, so those are your critical values. Now we need to find what the test statistic is and see if it falls in one of those shaded tails. Okay, we do that by running the TTest. So let's do this together. Hit stat. Scroll over to tests. Down to TTest and open that program. First thing it needs from us, it needs to know if we're going to be inputting data or if we're inputting stats. If you look up above, you don't see a list of the 17 salaries. You just see the stats on those salaries, like X bar, the mean of 22,000, and lowercase s, the standard deviation. So you need to run this off of stats. So open your t-test and make sure that stats is highlighted. Next thing it wants from us is mu sub naught, which is 30,000. Next thing it wants from us is x bar, which is 22298. Next thing it wants from us is lowercase s, or the sample standard deviation, which is 14,200. Next, it wants n for the sample size. It's tempting to put 16 there because you think degrees of freedom, but it doesn't say df, it says lowercase n, so give it the true sample size, which is 17. And the last thing you need to do is make sure that that does not equal sign is highlighted, and then you can run the program. Okay, for the critical value method, what we are interested in is the test statistic as the output t equals negative 2.24, approximate to 2 decimal places. I'm just going to switch colors so that you can see what I'm doing here. I'm going to put the negative 2.24 on the graph. It is further away from 0 than negative 2.12. And that means that our test statistic, that right there's the test statistic, TS for test statistic, falls in the rejection region. So our decision this time is reject the null hypothesis. Time to write our conclusion. We always start with the word there. Decision number 1, you have to say is or is not. When we reject the null hypothesis, we say there is. Then we write evidence to support. Oh, whoops, pause, getting ahead of myself. There is evidence to, and now it's time for the second blank. The second blank will either be the word support or reject. It is tempting to look at your decision to reject the null and want to put the word reject there. That is not where you want to look. You want to look back at the very original claim, which was equality, if you recall. And if our original claim contains equality, we use the word reject. Okay, there is evidence to reject, and then we write the claim that. And then we restate the claim. One town has a mean annual salary of $30,000. And I've run out of room, so I'm not going to write that, but do make sure you write the whole thing down when stating your conclusion. Okay, I'm going to go back to blue and point out the similarities as well as the differences in the p-value method compared to the critical value method. Okay, so they start the same. No graph necessary though. We go straight to the t-test. And we're looking for the output that says p equals. If you turn your calculator on, it's probably still on your screen. It's 0.0399, I'll go with, approximately. If you cleared your calculator screen, you'll run the t-test again using all the inputs that we did right here. So this would all be inputted into that test. Okay, the next thing we do for the p-value method is compare the p-value to the significance level, alpha, which in this problem is 0.05. and our p-value is 0.0399, which is lower than 0.05. Oops. So then we use that little rhyme. P is low, the null must go. All right, if the null must go, that means we reject it. Reject the null hypothesis. And the claim is exactly the same. There is evidence to reject the claim. I'm sorry, the conclusion is exactly the same. There is evidence to reject the claim that one town has a mean annual salary of $30,000. So there are your two methods side by side. I hope that helps you see the differences as well as the similarities in the two methods. And that will conclude our discussion on section 8.3. Thank you for joining me. See you next time to discuss 8.4.